Hello student, let us see what is electrostatic potential energy. Whenever you take a point charge, theoretically this point charge creates an electric field around it up to infinite distance. Means up to infinite distance electric field is created due to this point charge. Now everywhere in the point, since potential has been created at every point in the field, so whenever another charge QT is brought at any point in this electric field, we'll observe these two pair of charges will have some electrostatic potential energy. Now that electrostatic potential energy is given as Q1 Q2 divided by 4 pi epsilon naught R if we take free space. Now let us take how to find out. Suppose first example we'll take point charge. If I take a point charge plus Q. Now if I take point charge plus Q, then we'll observe theoretically up to infinity. Up to what distance? Up to infinite distance. We'll take up to infinity, which is created, electric field is created. Electric field is created. Now if we take any point in this field, suppose I take point number 1, we'll observe there will be some electric potential at this point 1. How to find out that electric potential? We'll just join it and I write down the electric potential at 1 can be given as equals to the charge Q1 divided by 4 pi epsilon naught. If R1 is the distance, then I can write R1. Now if I brought any other charge Q2, suppose a Q2 point charge is brought from where? From infinity. This is brought and placed at 1, right? Now if we bring plus Q2 from infinity to the point 1, then I can write down the work done by external latency in this process will be from infinity to 1 can be written as the potential of point 1 multiplied by the charge Q2. This can be written, and this will be written as Q1 Q2 by 4 pi epsilon naught R1. So I can say the electrostatic potential energy for 2 point charges, separated by R1 distance can be written as Q1 Q2 by 4 pi epsilon naught R1. This will be the electrostatic potential energy, and this electrostatic potential energy is stored in this field. Now, right? So let us see. This is for 2 point charges. If I take 3 point charges, suppose we want to find out what is electrostatic potential energy for 3 point charges. Suppose second example, take electrostatic potential energy for 3 point charges. Suppose I take 3 point charges are Q1, Q2 and Q3 are the 3 point charges. Let us take they are separated by distances R12, R23, R31. Now I can write down its electrostatic potential energy. How? By taking two point charges, by taking the pair of charges, and then we write down for pair of charges what is electrostatic potential. Will sum up for all the pair of charges, that will give you electrostatic potential energy. Now in this situation, for this we'll observe the first pair of charges is this one Q1. This is first pair. So I can write down first pair. The electrostatic potential energy will be Q1 Q2 by 4 pi epsilon naught R12. Now the second pair you will observe can be this one Q2 and Q3. For this pair, I can write down the electrostatic potential energy as Q2 Q3 by 4 pi epsilon naught R 2 3, and the third pair of charge can be this one. This is the third pair of charge for which we can find out the electrostatic potential energy. So for third, I can write Q3 Q1 by 4 pi epsilon naught R 1 3. So this is the total electrostatic potential energy for 3-point charges. Right. Now similarly, in case of 4-point charges, let us see how to find out the electrostatic potential energy for 4-point charges. Now in 4-point charges, we will get 6 pair of charges are involved. How the 6 pair? We will write down for all the 6 pair what is electrostatic potential energy. That will give you the total electrostatic. Suppose the third example will take electrostatic potential energy for 4-point charges. Let us take, for simplicity, we'll take the charges are at the 4 corners of a square. Let us take, these are the 4 charges. They are at 4 corners of a square. Now the first charge is plus Q1. Let us write down. Second one plus Q2, then plus Q3, and then plus Q4. These are the 4-point charges placed at the 4 corners of a square. Let us take this side is AA. For simplicity, we are taking the 4 sides of a square, and if we join these two, then this distance will be root 2a. Similarly, this will be also root 2a for this pair. Now here first pair, this is the going to be first pair. We can write down the electrostatic potential energy for the first electrostatic potential. We are going to write down for the system of 4-point charge electrostatic potential energy, or I can write U can be written as, the first pair is Q1 Q2 by 4 pi epsilon naught, and A is the distance. Similarly, the second pair will be this one. I can say Q2 Q3 makes the second pair. So for second pair, I can write Q2 Q3 by 4 pi epsilon naught A. Then the third pair can be this one, fourth charge and the third charge. So this can be the third pair. I can write Q3 Q4 by 4 pi epsilon naught A. Now the fourth pair can be the first charge and the fourth charge. This can be taken as the fourth pair. I can write down the for fourth pair Q4 Q1 by 4 pi epsilon naught A, and 2 more pair of charges are there. Which one? Now this Q1 and Q3 makes 1 pair, fifth pair, and then Q4 and Q2 makes the 6th pair. So for this I can write Q1 Q3 divided by 4 pi epsilon naught. Now not A, but separation is root 2a, so we'll write root 2a. And similarly for 2 and 4 I can write Q2 Q4 divided by 4 pi epsilon naught root 2a. So this is the total electrostatic potential energy for these 4-point charges system. We'll take 6 pairs of charges are coming, and we'll find out for all the 6 pairs of charges what is electrostatic potential energy. We'll sum up, and then the total electrostatic potential energy can be written like this. Now after from point charges, let us come to the spherical charges. Now first case we'll take, suppose a solid conducting sphere, metallic sphere is charged. How to find out its electrostatic potential energy? Now let us take the fourth example. We are going to take the fourth example as electrostatic potential energy of a charged solid conducting means metallic conducting sphere. Conducting. Now this electrostatic potential energy of a charged solid conducting sphere is also known as self energy of a charged body, of a charged sphere, I can say this, right? What is self energy of a charged sphere? What self energy is involved with a charged object? Now if I take a solid sphere, but this solid sphere is conducting one. Now if I take a conducting solid sphere, suppose this is center, what happens? Whatever charge is given to this, it all comes to the surface. Now let us take if Q charge, suppose if Q charge plus Q charge is given to sphere, then I can say potential of the sphere will be, potential of sphere will become Q divided by 4 pi epsilon naught R, if R is the radius, right? If R is the radius, then I can say potential of the sphere will become Q by 4 pi epsilon naught R. Now if dq charge is brought from infinity and placed on sphere, then the small work will be done as potential of sphere into dq. This can be written as q by 4 pi epsilon naught r times dq will be dw, right? Now if I want to find out what is total work done in bringing the q charge, suppose if sphere is given total charge as plus q, then I can write down the total work done. Total work done can be written as integral integral 1 by 4 pi epsilon naught r will be taken out. This is q times dq, and q varies from 0 to capital Q. So this can be written as q square. This can be written as capital Q square by 8 pi epsilon naught r. Now this is the total electrostatic potential, total electrostatic potential energy, or I can write, this can be also known as self energy also. This can be called as self energy of the charged sphere. Self energy, this can be written as how much? Q square by 8 pi epsilon naught r. If I take 1 by 4 pi epsilon naught as k, then I can also write down k q square by 2r, where k stands for how much? 1 by 4 pi epsilon naught r. So this is the self energy of a charged conducting sphere. How much is self energy? Self energy can be written as k q square by 2r. Now if I take a charged spherical cell, suppose I take a charged spherical cell and it is given a q charge, then what is its self energy, or what is its electrostatic potential energy? That will be same as the solid conducting sphere. So fifth example we'll take, suppose I take a charged spherical cell and then I want to find out what is its electrostatic potential energy. How to do it now? Next example, the sixth example is, I can take charged spherical shell. I take cell. Now suppose I take a cell which is charged by Q amount. Suppose this is a spherical cell, this is the center, and the cell means a thin layer, right? This is a cell, and now this cell is given Q charge. I want to, what is its electrostatic potential? This will be same as the charged solid conducting sphere. I can write its electrostatic potential energy is given as Q square K Q square by 2, if R is radius, I can write 2R, or I can write Q square by 8 pi epsilon naught R is the electrostatic potential energy for a charged spherical cell. Now if I take 7th example, suppose I take a non-conducting spherical cell. Suppose we take 7th example is a charged non-conducting sphere. What is its self? That is known as self energy of a charged non-conducting sphere. Now in case of non-conducting sphere, what happens actually? Now if you take non-conducting sphere, you will observe this is center. Whatever this Q charge is given to it, whatever Q charge is given to this non-conducting, it spreads in the volume. It spreads in the volume of the non-conducting sphere, right? Spreads inside it, and then its energy, suppose this is a non-conducting, maybe made of glass, mica, non-conducting materials, and Q charge is given to this solid non-conducting sphere. I want to find out what is its electrostatic potential energy. Now what is its self energy? Now its energy can be taken in two parts. First part is the energy is stored here. I can write down the total electrostatic potential energy, U total, can be written as the energy stored for region x is equal to R to x equals to infinity, plus energy stored in the region x equals to 0 to x equals to R. Right, this is the total energy. This total energy can be written as whatever energy is stored in this region, x equals to R, means from the surface up to infinity. What is energy stored in this region, and what is energy required to make this one? In this region, what is energy stored? Now, how can I write down? Now, energy stored in this region, outside this, x to R to infinity, same as electrostatic potential energy of a charged solid sphere. What was its value? Its value was simply written as Q square by 8 pi epsilon naught R, plus energy stored from x0 to x equals to R. Now how to find out this energy? To find out this energy, I will take a x distance, I will take a Gaussian surface. Now here I will write down the electric field. Electric field at x can be written as the charge stored, let us take the small q charge stored in this x radius of the sphere divided by 4 pi epsilon naught x square. So this is electric field. Now if you just increase this electric field, if you just increase this radius x to dx, x to how much? Dx. This is the dx. Now if I increase this, then the volume increased will be, dV will be written as 4 the surface area of the elemental solid is 4 pi x square, and increase in thickness is dx. So this is the volume. Now the small energy density can be written as, or let us write down the small potential energy stored in this one can be written as 1 by epsilon naught times Ex square times Ex square times dV. Now this can be written as half epsilon naught. Ex square can be written as q square by 16 pi square epsilon naught square. This will go x4 d4 pi x square dx. Is it? Now we want to write down what is q, what is the charge stored in the sphere of radius x. Now q can be I suppose the volumetric density q is the total charge. Then I can write volumetric density is in form 4 by 3 pi r cube equals to q by 4 by 3 pi x cube. So I can write down the q in nothing but q by r cube times x. Now I can write down this small potential energy stored in that elemental thickness dx can be written as half epsilon naught. Now q square can be replaced by this one, q square x square. This will be r6 q square, then 16 pi square epsilon naught square x4, and then dx can be written. Is it clear? Is it clear? Q can be written like this. Dx. Now I can cancel 4 pi. This is x cube, sorry, this is not x, this is x cube. So this can be written as x6 by r6, and then this value can be 16 pi square x square dx, and then 4 pi x square dx. There will be 4 pi x square will also come, and dx. Now this can be cancelled. 4 can be cancelled with this. I can write only 2. So this can be written as half epsilon naught q square divided by 16 pi square epsilon naught square r6, and then this is 4 pi, and when I x square x4, I will integrate for x 0 to r, so x 5 by 5, so this will be r 5 by 5. Is it? Now I can write down the total energy with this much. So total electrostatic potential energy from x0 to x equals to r can be written as this 4 pi gets cancelled, 4, this will come 4, 5, 10, so 40. I can write down this value as this r5 gets cancelled with this. I can write down this epsilon gate also gets cancelled with this one. So I can write q square by 40 pi epsilon naught r. Now I can find out total energy as now I can write down. I can write down the total energy is now written here. How much? We'll write down this is 8. This value I can write q square by 8 pi epsilon naught r plus this value comes as q square by 40 pi epsilon naught r. Now this will 48, say this will become 3 by 20, right? Q square by pi epsilon naught r. So this is the total electrostatic potential energy of a charged non-conducting sphere. 3 by 20 Q square by pi epsilon naught r. So this is the value of electrostatic potential energy for a charged conducting sphere 3. This can be also written as, if I take K as, yeah, we can leave it 3 by 20 Q square by pi epsilon naught r. Now, if I take, suppose I want to find out by 20 for non-conducting and 1 by 8 for conducting. Now let us take another example, 8th example, right? Now if I am taking two non-conducting, suppose this is a non-conducting sphere of radius A and charge Q1 is given. This is A. Now from its center another is placed, another non-conducting sphere of charge Q2 there and radius B, and the separation between these two are D. This is two charged non-conducting solid sphere. I want to find out what is its electrostatic potential energy. Now here the electrostatic potential energy can be written as total as the U self energy of, suppose, sphere A plus, this is suppose B. Now plus U self energy of sphere B, plus third one will be U interaction as a point charge, interaction energy of A and B. How can I write? Now this can be written as the self energy of A. Now we have find out 3 by 20 Q square by pi epsilon naught, its radius is A, plus for B the self energy can be written as Q2 square by 3 by 20 Q2 square by pi epsilon naught B, and when you treat them as a point charge, then they are separated by d distance. So Q1, Q2 by 4 pi epsilon naught, and separation is d. I can write down. Is it? This is for this two. I can write down electrostatic potential energy for two non-conducting solid charged sphere, separated by distance d. This is the value. Now let us take another example. If I take the 9th example, I take, suppose I take a charged sphere is, let us take, this is a radius A, this is given Q1 charge, and there is a cell around it. Of radius B, and this is given Q2 charge. I want to find out for this also what is the electrostatic potential energy. Now here also we'll observe for, I can write down A electrostatic potential energy for inner sphere, total